Suppose E represents Earth and this is a small stone of mass 50 kg. Fine, as compared to the Earth, this is very small. And you have dropped this stone from a certain height. Obviously, the stone is going to move towards the Earth. Now, if you calculate what is the force between the stone and the Earth, for this, we have to use this formula. Now, suppose capital M is the mass of the Earth, small m is the mass of the stone, and r is the radius of the Earth. Now, we know the relation F equal to G, m into small m by r square. You put the values, capital G's value you know, 6.67 into 10 to the power minus 11. Capital M is this one, small m is 50 and r square is this square because this is the radius of the Earth. Now, if I calculate 6.67 into 6 into 50 and this 10 to the power minus 11 and 10 to the power 24, if we write like this, we are going to get 24 minus 11 because bases are same, powers will be subtracted, it will be 24 minus 11. And here 6.4 square means 6.4 into 6.4 into 10 to the power 6 to the 12. So if you calculate, you are going to get approximately 488. We can consider it is 500 Newton. Now, what is the acceleration produced in case of stone and in case of Earth? Now, if you want to calculate what is the acceleration produced in case of Earth and in case of stone, because whenever we drop, it is observed that the stone moves towards the Earth, but Earth never moves towards the stone. It is so, both of them are experiencing the same force. Now, we know F equal to ma from Newton's second law. So, acceleration will be force divided by mass. Force is 500, already we have calculated, and mass is 6 into 10 to the power 24. This is the mass of the Earth. So, if you calculate, you are going to get approximately 83.3 into 10 to the power minus 24. So, it's a very small quantity, 10 to the power minus 24 meter per second square. Whereas, in case of stone, F equal to ma2. So, a2 will be F by m. Force is 500. Mass of the stone is 50. 10 meter per second square. So, if you compare these two, you can see the acceleration produced in case of stone is much more as compared to the acceleration produced in case of Earth, which is negligible. That's why whenever we drop a stone, stone moves towards the Earth because here acceleration produced in stone is more as compared to the Earth. That's why Earth never moves towards the stone. I hope this concept is clear. What are the effects of force of gravitation or importance of universal law of gravitation? Number one, it is the gravitational force between the sun and the Earth which makes the Earth move around the sun with uniform speed. And every day, every moment we are experiencing it. So that means a very important force. The tides which are formed in sea or in ocean, this is also because of the gravitational pull exerted by the sun and the moon on the surface of Earth. It is the gravitational pull of the Earth which holds our atmosphere in place. These are some important effects of force of gravitation. Clear? When we consider one very big object and another one very small object, then whatever the force of gravitation is there, that is termed as force of gravity. That means force of gravity is a special case for the force of gravitation when one among the two bodies has an infinitely large mass as compared to the other. So if you consider the mass of the Earth and the mass of the stone, you will find that the stone is negligible as compared to the mass of the Earth. Then the force between Earth and the stone is termed as force of gravity. Clear? Now from Newton's second law, we know force equals to mass into acceleration. Force equal to mass into acceleration. Whenever we drop something, it moves towards the Earth with certain acceleration. That is termed as acceleration due to gravity, and we write g. That means whenever a stone is dropped, it must have some acceleration, and that acceleration, we instead of a, we use the letter g, and this g represents acceleration due to gravity. Clear? So instead of F equal to ma, in gravitation we use F equals to mg. Fine. Now let me discuss the relation between capital G and small g. Suppose let us consider a body on the surface of the Earth. such that small m is the mass of the body and capital M is the mass of the earth. R is the radius of the earth. Because the object is very close to the earth, we can consider the distance to be r. Fine. And whenever we drop the thing, object will move towards the earth. Suppose g is the acceleration due to gravity. That means whenever object is dropped, it will move towards the earth with certain acceleration, and that acceleration is small letter g. Now from Newton's second law of motion, we know force equal to mass into acceleration, so we can write F equals to mg. Clear? Again, if you use Newton's law of gravitation, then you are going to get F equals to capital G, capital M, small m by r square. This relation you know from Newton's law of gravitation. Now both the forces are same. Since both the forces are same, I can write mg equals to gm small m by r square. This small m can be cancelled. You are left with g equals to gm by r square, where this small g is the acceleration due to gravity, and capital G is the universal gravitational constant. This is the relation between small g and capital G. Now G equal to gm by r square, as G capital G is a constant, mass of the earth is also a constant, so we can say G is inversely proportional to square of the radius of the earth. Clear? That means more the radius, less will be the value of G, and less the radius, more will be the value of G. Let me discuss this one in detail. We know our earth is not perfectly spherical. Radius along the equator is little bit more as compared to the radius along the pole. So this is the pole, this is the equator, and it is found that this radius is approximately 21 km more as compared to this one. So that means along equator radius is more, and along pole radius is less. So radius along equator is more than radius along pole, and we know G proportional to 1 by r square. That means when radius is more, G will be less. Therefore value of G in the equator will be less as compared to value of G near pole. The next topic that we are going to discuss is mass and weight. In case of mass, what is the definition of mass? It is the amount of matter contained in a body. That means if I say the number of particles in this pen, suppose, wherever you go, number of particles will remain same. That means it is a constant quantity. Whenever we say mass, its SI unit is kg, and it is measured by physical balance. In case of weight, whenever we drop something, then earth attracts it towards its center. The force with which earth attracts everything towards its center, that force is called weight. As we know, the acceleration due to gravity is different at different places. In pole, G is more. In equator, it is less. So weight varies from place to place. Newton is the SI unit of force. So SI unit of weight is Newton, and it is measured by spring balance. So these are the basic characteristics of mass and weight. Now when we say weight, as I told you, weight is the force. So we know F equals to ma. So since weight is nothing but the force, so we can say W equals to mg. So this is the relationship between weight and mass. We often confuse with the word weight and mass. Weight and mass are not the same thing. Whenever we drop something and the object moves only because of gravity and no other force acts on it, then whatever acceleration is produced, that is called acceleration due to gravity. So acceleration due to gravity at a place, whenever it is multiplied by mass, then you are going to get weight at that particular location.